Hi, I'm Ryan Baker, and this is Big Data Education. Today, we're going to continue our relationship mining week by discussing association rule mining. In association rule mining, we try to automatically find simple if-then rules within the dataset. The classic example, famous and fake, is that people who buy more diapers buy more beer. So if person X buys diapers, then person X buys beer. Simple if-then rule. The conclusion? Put expensive beer next to the diapers, because that guy who's going to get diapers is going to buy beer, so get the really expensive good stuff there so he'll buy that. Now, as with anything, there are multiple interpretations for this rule, and it's important to keep that in mind. For example, it might be that a guy is sent to the grocery store to buy diapers, he wants to have a drink down at the pub, but he buys beer to get drunk at home instead. But it also could be that there's just no time to go to the bathroom during a major drinking bout. I'd like to bring up a serious issue with association rule mining, and especially relevant to the previous lecture. Association rules apply causality by their if-then nature, but causality can go either direction. Now, when we make real association rules, the if conditions can be more complex. For example, you could say, if person X buys diapers, and person X is male, and it's after 7 p.m., then person Y buys beer. Or it might be that the then conditions can be more complex. If person X buys diapers, and it's person X is male, and it's after 7 p.m., then person Y buys beer and tortilla chips and salsa. Complex then conditions can be harder to use in practice, so they're often eliminated from consideration. Association rules are useful for a lot of things. First of all, they're useful for generating hypotheses to study further. Along those lines, they're also useful for finding unexpected connections. For example, is there a surprisingly ineffective instructor or math problem? Or are there e-learning resources that tend to be selected together? So association rule mining, what's the process? First we find rules, then we evaluate the rules. I'll talk first about the procedure for evaluating the rules, because it actually influences the procedure for finding them. So, what would make a rule good? Well, the first thing is a metric called support or coverage. And the second one is a metric called confidence. And the third one is a set of metrics that are collectively called interestingness. Let's talk about support/coverage first, and I'm calling it support/coverage because it's called by both names in different papers. This is the number of data points that fit the rule divided by the total number of data points. A variant is just the number of data points that fit the rule. It actually isn't a big deal either way. So let's look at an example. Let's say we're investigating the rule, if a student took advanced data mining, the student took intro statistics. What's the support or coverage on this one? Well, we can count the number of cases where they're both true. So it turns out that the support coverage is 2 cases out of 11 cases, which is 18%. Confidence. Confidence is the number of data points that fit the rule divided by the number of data points that fit the rule's if condition. So if the if condition isn't met, we don't care at all for confidence. We only care how many of the ones that fit the if also fit the then. This is equivalent to precision in classification. It's also referred to as accuracy by some association rule miners, just to make things really confusing, because it's not at all the same as accuracy in classification. I call it confidence, most people call it confidence, just because they don't want to clash heads with the classifying people. So let's look at an example. Same example as before. We can say, what's the confidence? Well, to find the confidence, we're first going to look at the students who meet the if condition. Did the student take advanced data mining? And of those, there are 6. Then we'll say, how many of those 6 also took intro stat? And it turns out that 2 did. So 2 out of 6 is 33%. So we have a higher confidence than we have a support. That's actually fairly common, especially if you have a lot of things going on in your data set. You might have very low support for anything, but have relatively high confidence for some things. So one thing that's important to note is implementations of association rule mining sometimes differ based on whether the values for support and confidence and other metrics are calculated based on exact cases or some other grouping variable. And this grouping variable is sometimes called the customer in specific packages, like RapidMiner. For example, let's say you're looking at whether boredom follows frustration, and you're investigating the rule if frustrated at time n, then bored at time n plus 1. For example, if you ignore grouping, confidence is 4/5. 5 of these cases fit the if case, and 4 of them fit the entire rule. But if you treat student as your customer grouping variable, then the whole rule applies for A and C, and if applies for A and C. So your confidence is 1. Now, let's talk about arbitrary cutoffs for a minute. Now, what's a good support? What's a good confidence? Well, the association rule mining community differs from most other methodological communities by actively acknowledging that cutoffs for support and confidence are completely arbitrary. That's so cool. Researchers typically adjust these two to find a desirable number of rules to investigate, ordering from best to worst. So in other words, if you try an initial support and confidence cutoff and you're not getting enough examples, then you lower them and you try more. If you're getting too much, you raise them. What a neat idea. And they do this rather than arbitrarily saying that all rules over a certain cutoff, kappa 0.6, p of less than 0.05, are good. So support and confidence are not the only metrics out there. They're not enough. And why not? Because it's possible to generate large numbers of trivial associations. I'm going to give you a couple examples that have really been published, and I'm going to redact the author names because I'm making fun of them. One author found that students who took a course also took its prerequisites. At a university where that was actually a requirement for taking the class, and you couldn't just sign out of it with the instructor's permission. Wow, whoever would have guessed. Another published finding. If you do poorly on the exams, you'll probably fail the course. Gee, could that be because the exams actually are computed into your course grade? See, association rule mining without much domain knowledge can lead to pretty trivial findings. And that leads us to thinking about interestingness. Interestingness is not quite what it sounds like. It's typically defined as just any measure other than support and confidence, rather than an actual measure of the novelty or usefulness of a discovery, which, to be fair, would be a real pain to create. So, Merceron and Yosef talk about some potential interestingness measures, and they recommend two for educational data mining, cosine and lift. Cosine is the probability that the if and the then occur together, divided by the square root of those two probabilities multiplied by each other. And this measures co-occurrence. Merceron and Yosef note that it's easy to interpret. Numbers closer to 1 than 0 are better, and they say over 0.65 is generally desirable. Another interestingness measure that Merceron and Yosef recommend is lift. That's the confidence divided by the probability of the then statement. This measures whether data points that have both A and B are more common than data points only containing B. And they notice again that it's easy to interpret. So their recommendation is that rules with high cosine or high lift should be considered interesting. And I've actually in my group had some results that seem to indicate that that's a pretty good rule of thumb. Works pretty well. There are other interestingness measures. Tankumar and Srinivasta talk about 21, although one of them actually turns out to be identical with something we've already seen before, so I left that one out. And there's a bunch of them. Again, cosine and lift have been recommended by Merceron and Yosef. If you know what you're doing, maybe you want to look at the Gini index. Maybe you want to look at Yule's Q. If you don't, I would say go with what Merceron and Yosef say. It's a reasonable rule of thumb. Nothing wrong with it. Now, it's also worth drawing your attention to the Jacquard metric, which measures the relative degree to which having A and B together is more likely than having either A or B, but not both. Another thing that people do sometimes, although they don't do it all that much, is they select rules based both on interestingness and on the rule you select being different from the other rules you've already selected, or in other words, involving different operators. So try to find rules that explore the space more thoroughly, rather than finding a whole bunch of rules involving something that's pretty common. Now, an alternate approach to interestingness was proposed by Basel Dua and colleagues. They compared interestingness measures to human judgments about how interesting the rules were. So in other words, with these measures we say, this is interesting, but does it actually match to what a human being thinks is interesting? They found that Jacquard and cosine were the best single predictors, and that lift had predictive power independent of them. So broadly, this is much what Merceron and Yosef said. But Basel Dua and his colleagues found that the correlations between Jacquard and cosine on the one hand and human ratings of interestingness were negative. And for cosine, this was the opposite of what Merceron and Yosef had to say. So in other words, the issue of what human beings find interesting is complex, and it might not be quite the same as what our interestingness measures indicate. It's an open debate in the field as to which the best way is to evaluate your association rules, but these are some reasonable guidelines, and you won't go all that wrong if you use them. So, we've talked about evaluating rules. Now let's talk about finding rules. Probably the most popular way to do this is the a priori algorithm, where you generate a frequent item set, and then you generate rules from that frequent item set. So let's look at how you generate the frequent item set. You take all single items, and you take those with support over a certain threshold. Then you generate all pairs of items from items in the set, and you take those with support over the threshold. So you can take all the pairs that are more common than your minimum. Then you generate all triplets from those items, and you take those with support over the threshold. And you just keep doing this until you don't come up with an item set that has anything with support over the threshold. And then you form the joint item set of all item sets. So anything that was frequent enough, you're going to keep. You're going to put them all together. Length 1, length 2, length 3, and so on. Then you generate rules from that frequent item set. So given a frequent item set, take all the items with at least 2 components, so we're going to throw out the singletons, and generate rules from these items. So ABCD will give you ABC predicts D, ABD predicts C, AB predicts CD, and so on. Then we'll eliminate all the rules with confidence below the threshold. So finally, rank the resulting rules. You have a bunch of them using your interestingness measures. Other algorithms beyond a priori typically differ primarily in terms of the style of search for rules. One variant on association rules is negative association rules. So what doesn't go together? That's especially interesting if probability suggests that 2 things should go together. So perhaps people who buy diapers don't buy car wax, even though 30-year-old males buy both. Or perhaps people who take advanced data mining don't take hierarchical linear models, even though everyone who takes either has advanced math. This is actually something you see in the real world. Maybe students who game the system don't go off task. Actually, it turns out that despite these both being disengaged behaviors, which are associated with a lot of the same student attitudes, students who do one don't typically tend to do the other. And this is true both among individual students in a class, but also true between countries. There are whole countries, like the Philippines, where students game the system a lot and rarely go off task, and whole countries where students go off task a lot, but don't game the system nearly as much. So that's association rule mining. In the next lecture, we're going to talk about a close relative, sequential pattern mining. So I'm Ryan Baker. This is Big Day in Education. Thank you very much. See you next time.